Hey guys, welcome to Chapter 2, Section 7, Graphing Techniques. And this video is going to be broken into two parts for your viewing convenience. The chapter itself is pretty intensive, so we'll kind of break it up into a couple of pieces. Okay, so studying transformations is kind of the best way to draw graphs based on the basic parent functions that we saw in the previous section. So things, for example, like in example 1, we're talking about the absolute value function, which you know roughly makes a V shape and starts out something like this, right? So the absolute value of x, my y value. So we have something like -2, -1, 0, 1, and 2. And on this side, when you take the absolute value, you would get, of course, the positive versions of that, okay? So by adding this 2 in the front, the graph is being stretched by a factor of 2 vertically. And so what we're going to do is we're going to keep everything the same for the x values, but we're going to change our y values to be twice as large. So we're going to do 2 times our y values. So just copying my x values down, and we're going to have 4, 2, 0, 2, and 4. Okay, and so this graph will be, of course, stretched out compared to the original graph. And we'll just graph both on this one just so we can see it. So if we were to graph the original absolute value function looks something like this. And then our stretched version that we just came up with is going to look something like this instead. So you can see it is skinnier and definitely accelerating upwards a lot faster than the original version. Okay, and the 1/2 in the other spot there is going to do the exact opposite, and we're going to multiply the y values by 1/2, which will actually scale them down and make them shrink. So again, the x values have not changed in any of these, and so we're going to leave that alone, but I'm going to do 1/2 times the y values. Okay, so these are going to be something like this: 1, 1/2, 0, 1/2, and 1. And we can kind of graph that. And you can see your graph is going to look a little bit wider, and it's going to be kind of flattened out compared to the original graph. Okay. And so these transformations that are being multiplied onto the front here are respectively a vertical stretch and a vertical shrink. And you would, of course, state by how much, so it would be a stretch by 2 or a shrink to 1/2. Okay, so you should be pretty familiar with your transformations from your study of Algebra 2, and we're going to use some of those same concepts you've seen before in the next few problems. So continuing this time, we've got one more example using that absolute value. And so this one is kind of interesting because this is a horizontal change, and it's going to affect my x values. But this is a shrink, even though it says times 2. Okay, so keep in mind that when you set up a function, the inside, which changes your x values, is always backwards. So this is always doing the opposite of what it says. So we should actually divide by 2, not multiply by 2. Okay, and it's kind of an interesting point that this happens, but a convenient way to remember it, if the transformation is happening to your x values, i.e. it's a horizontal change, you should always be doing the opposite of what you are shown in that equation. And so in this case, it says times 2, we're going to actually divide by 2. Okay, and the handy way to remember this is, remember, your exes, your ex-boyfriend or ex-girlfriend, they were lying to you, and these exes are also lying to you. They are definitely telling you the opposite of what you should be doing. Okay, so I'll just copy down the original again, just so we can have it in front of us, and we'll go ahead and divide it by 2 in just a moment. So this is, of course, just the parent function. You can find these coordinates in your section 2.6 notes as well. Okay, so what we will do is we're going to do x divided by 2. And we're going to leave the y values all alone in this case. The y is, of course, the absolute value of x. So we're going to have -1, -1/2, 0, 1/2, and 1. And we will see this is going to be 2, 1, 0, 1, and 2. And so when you graph this, it's actually, interestingly enough, is going to look very similar to what we saw from a vertical stretch, even though the points are a little bit closer together. You're going to see it's the exact same as if you had put a 2 on the outside versus on the inside. So it is, of course, a horizontal shrink, which means as you push the graph together, it, of course, gets taller. Now, these green boxes here are a nicer little reminder about this. And it just mentions, hey, if you see a value that is greater than 1 in front of your function, you know that's going to be a stretch. If it's a fraction or a smaller number, it will be a shrink. And then the horizontal is, of course, the reverse of that. Okay, so this was an example of a horizontal shrink. And remember that it is the opposite of what's happening in the equation. Okay, so when you look at it and you see, oh, times 2, but since it's inside of those absolute value lines, it's doing the opposite to the x value. Okay, looking at how to reflect your graph, and there's two kinds of reflections. Of course, one is over the x-axis and the other is over the y-axis. Okay, and so this first one where we have this negative on the outside is going to be a reflection over the x-axis, right? So this is reflect over x-axis, okay? And changing over the x-axis means your y values are going to be the ones to change, okay? So we'll just start with the basic square root function, original. And we're going to pick some convenient numbers that are very easy to work with. So 0, 1, 4, and maybe 9. And so when you take the square root of those, 0, 1, 2, 3, okay? And if we graph that, you can see, hey, it makes this curve going like this, okay? And the reflected version of this, of course, is going to not change your x's, but change your y's, because again, this is outside of that square root sign. So it makes my y values negative. My x values will stay the same. 0, 1, 4, 9. The negatives on the y values, 0, -1, -2, -3. And what you're going to see is this graph is actually a mirror image. It's outright just flipped over the x-axis. Okay, and so by adding that reflection, adding that negative, my graph has flipped over. And you can see that this change is vertically, that reflection over the x-axis is going to change only your y values. Okay, and the second example is actually the opposite. We're instead going to change our x values, and it's going to reflect over the y-axis, okay? And if you want, take a moment and speculate what's going to happen with this, okay? So again, I'm going to start with this original that I have here in black, and let's see what our new points look like. So the negative being on the inside is going to change the sign on my x values and leave my y values unaffected, okay? So again, I'm taking from this black set of numbers and we're going to pull them down here. And so we've got 0, -1, -4, and -9. And my y values are 0, 1, 2, and 3 again. Remember, I'm picking these y because these are easy numbers to square root. Okay, and so let's see what our graph looks like. So 0, 0, -1, 1, -4, 2, and -9, 3. And so now if you connect this, you see, oh, look, my graph's going in the opposite direction. and that is a reflection over the y-axis, okay? So again, the reflection over the y-axis is going to change your x values, okay? And the reflection over the x-axis changes the y value. So whichever axis you're shifting over, you're going to actually transform the opposite values. Now remember, inside always affects the x values. So right, anything in here is going to change your x, and anything out here or in the back will change your y values. Okay, so that is a handy way to keep in mind. This applies to all functions. Any behavior that is on the outside of the parent function, in this case it's a square root, that affects your y's, and then anything on the inside will change your x values. Okay, and so this is an example of reflections, which is the second transformation we're talking about now. Okay, so a quick reminder that the outside reflection is going to be across the x-axis and the inside negative makes it across the y-axis. They show you kind of using algebra. They're showing you, hey, xy and x negative y, showing a flip over the x-axis, and you are changing the y value, and vice versa here, negative xy from xy. Now, below you'll see a pair of graphs which are demonstrating symmetry. And so we are going to measure symmetry across some of the different axes, both the y-axis and the x-axis. And so what you can see is across the axis, you should be able to find a corresponding point where either the x value matches up and the y value does not change, or vertically, the x values are the same, but we have opposite y values, okay? And so basically, the idea is that symmetry, the graphs can be folded in half across one of these axes, okay? Perhaps even both, okay? So what we're going to do is we're going to go and we're going to check out how we can algebraically tell if there is symmetry. Okay, let's take a look at how to algebraically prove symmetry. And what we do here is we replace x with negative x to test if we have symmetry with the y-axis. And when we test symmetry with the x-axis, we just do the opposite, and we're going to replace y with negative y, okay? And the idea is if these are actually symmetrical, then the resulting equation from one of these operations will be the same as the original equation that we started with. So let's start with A, okay? And what we're going to do is we're going to make a little bit of a testing chart here. And how I'm going to do this is I'm just going to put the original equation here, y equals x squared plus 4. Okay, and the goal is just going to remain, can we get the next equations to match this based on what we plug in, okay? And so let's start with the x-axis symmetry. And in order to get x-axis symmetry, we would plug in negative y, okay? So we're going to replace negative y instead of that y that we had originally. So here we go, negative y equals x squared plus 4. And if we simplify this, let's say we just move this negative back to the other side, just to get y by itself. And I get this, y equals negative x squared minus 4. But this is not the same as this, right? Let's note this is not the same, okay? And so from here, we can kind of say this is not going to be true, okay? And we can go on to our next test. And so let's look at y-axis symmetry. Okay, so for y-axis symmetry, remember, we're now going to plug in negative x instead of x. So what it looks like is something like this, y equals negative x. Now notice that squared is affecting this entire piece, okay? And that dramatically is going to change what happens. So here, when we square this, we get y equals x squared, because the squared cancels out the negative, plus 4. And this is actually the same as my original equation. And so what we discover is that this function has y-axis symmetry. but it does not have x-axis symmetry because that one did not match when we plugged in the value. Okay, so whichever axis of symmetry you are testing, you plug in the opposite variable as negative, and you see does it match up. Okay, on a graph, this would show that you could fold the graph in half along the y-axis, and you have a point that is xy that matches with negative xy. Okay, so let's try this one more time. Let's go down to part B, okay? And again, the idea is to see if when you plug in a negative, do you still get the same equation, okay? So let's make our little testing chart here and just copy this one the same way it is down here. X equals y squared minus 3. And let's do our x-axis test first. So we're going to plug in negative y, okay? And so again, we just go to our equation, we rewrite it, but we use negative y instead of normal y. And what's going to happen is, again, you see there's a square on this y, and squares tend to cancel negatives. So what you'll see is these are now matching, so this actually checks out. Okay, and then we can do our other symmetry test the same way and do our y-axis symmetry test. Okay, again, now we're going to plug in negative x this time instead of negative y. It's the opposite of the axis, remember, okay? So negative x equals y squared minus 3, and you'll quickly discover this is not the same, okay? So if it does not turn back into the original, you know that that is not going to apply, okay? And so what we discover from this one is that it has x-axis symmetry in this case. Okay, so again, what we're doing is we're showing that by plugging in negative y, the equation is actually equal to the original equation, showing that there's a point, negative y, which matches up with a x value, the same x value that the positive y had. Okay. All right, let's take a look at C. This one's going to be kind of interesting. Go ahead, pause, set it up yourself if you want, and see if you can tell what symmetries this has. Okay, and so if you tested it out yourself, there's a great way to check your work. X squared plus y squared equals 16. Let's start with negative x, which is going to be my y-axis symmetry. Okay, and you might notice that the square is going to give me negative x squared plus y squared equals 16. And that is just x squared plus y squared equals 16. Okay, so this one seems to check out because the square cancels out the negative. Okay, and let's check out our other one. So we're going to have x-axis symmetry, which means, of course, we do the opposite. Let's plug in negative y. And when we fill this in, you'll see, hang on, x squared plus negative y squared. Again, this parentheses is super important. Okay, and that turns back into x squared plus y squared equals 16. Okay, and since this is the same as the original, this one also checks out, and this graph has both x and y-axis symmetry. Now, symmetry is very tricky at times, so keep in mind what you're testing. Plug in the opposite variable of your axis as a negative, and always compare it back to your original function, okay? So the goal is to see if this matches up with the original. If it matches, you've got that symmetry. If it doesn't match, it's not going to have that symmetry, okay? Here's example D about testing for symmetry with respect to an axis, okay? If you're feeling confident about it, go ahead and give it a shot yourself, okay? And what we're going to do is, again, copy your original equation down here. And we're going to plug in negative x for our y-axis symmetry and negative y for our x-axis symmetry, okay? So here we go. Let's start with negative x. So 2 times negative x plus y equals 4. And we got negative 2x plus y equals to 4. No, that's not going to work, right? This is not going to be the same as this, so we can throw that one out. And if we go on to negative y, 2x plus negative y, and again, I'm just putting the parentheses in to clarify where we're putting this negative, okay? And basically you get this, 2x minus y equals 4. And that's, of course, not the same as this. So this one also is thrown out. So this does not have either of these symmetries, okay? So again, this was y-axis, and this one is x-axis symmetry, okay? So this one has neither of these, okay? And you can kind of see the visual of some of these. So showing you x-axis and y-axis symmetry, okay? And you can see these are actually some of the previous problems that we just worked out. So if you're better at visualizing what these graphs look like, you can also visually see the symmetries, right? Like there's a matching point here and here on this graph across the x-axis, okay? All right, there's one bonus type of symmetry, which is symmetry with respect to the origin. And if you've ever looked at inverse functions, this comes up with inverses a lot, okay? And so let's take a look at how we can prove that, okay? So testing for symmetry with respect to the origin, well, it's the same idea as testing for symmetry with the respect to any of the axes. We do it kind of the same way. So again, first equation is the original. Okay, and when you want to test origin symmetry, well, we did negative x and we did negative y previously, so now we're going to do both, negative x and negative y. Okay, so this is for origin symmetry. And so when we plug this in, negative x squared plus negative y squared equals 16, and you just get, oh, this is still just x squared plus y squared equals 16. And this is the same. So this one has origin symmetry. Okay. And it really is that simple. It is just like plug the negatives in, see if they cancel out. If they don't cancel out, it's not going to work. Okay. All right. We got a couple of examples here. So let's take a look at the next one. So y equals x cubed, same idea. Let's set it up. And this one's a pretty simple one. Y equals x cubed. Let's plug in negative x and negative y. So negative y equals negative x to the third power. And hey, an odd exponent will keep the sign, right? So when we simplify this, something interesting happens again. So we get negative y equals negative x cubed. And when we take this a step further, these actually cancel out. And we get y equals x cubed. Well, what do you notice about that? It's the same as what we had here. So this function, again, has origin symmetry. Okay? Remember, if it fails the test, then it doesn't have origin symmetry. And now you've seen all the types of symmetry, x-axis, y-axis, and origin. Those are the three different kinds. And so the test is basically the same thing. It's just the question of what are you going to plug in as a negative. And remember, if the equation does not come out the same as the original, that just means it doesn't have that type of symmetry. Okay, so talking a little bit about even and odd functions. And so essentially it's connected very much with symmetry. And so functions that are even have symmetry with respect to the y-axis. And so the test for them is actually the exact same. Okay, and then the same thing is true with odd functions. They have symmetry with respect to the origin. Okay, so the test is going to work the exact same way. And what we'll do is we'll come to our function and let's set it up. So remember, the goal is to get it to match the original And the original in our case says y equals 8x to the 4th minus 3x squared plus 1. Okay, and so let's start with if this function is even. Okay, so the even function is going to have just negative x. Okay, this is the even test. Okay, and so what we'll get when we do this, we're going to have y equals 8 negative x to the 4th minus 3 negative x squared plus 1. And again, since these have even exponents here, those signs are actually going to be disregarded. So this is going to stay minus 3x squared plus 1, and you're going to realize that this one checks out, that it is an even function. Okay? And we can do the same test with this for if the function is odd. Remember, odd is origin, so we're going to do negative x and negative y. And basically, as soon as we plug in this negative y and we see, wait a minute, that negative is not being balanced on the other end, you're going to understand that this is not going to be an odd function. Okay? And so basically, you get a negative, but this side, all the signs canceled out. And so you get the opposite of what you actually wanted. And so this one is not going to have this symmetry. And it is not an odd function. So this would be described as being an even function. Okay, so even and odd is more vocabulary than anything else. It is the exact same as if you were talking about symmetry. Some more examples here. Here are a few more examples of testing if a function is even or odd. Okay, so we can say, hey, y equals 6x cubed minus 9x. Let's go ahead and try negative x to see if it's even. Okay, y equals 6 negative x cubed minus 9 negative x. And you're going to see these do not cancel out because of those odd exponents. So negative 6x plus 9. And you'll see these are actually opposites of one another. That's kind of a good sign for this being an odd function, actually. So let's see if that actually does check out. So if we were an odd function, we're going to have negative x and negative y. So negative y equals 6 negative x cubed minus 9 times negative x. Okay, and basically this side we've already done once, so negative 6x cubed plus 9x equals negative y. And when I flip all my signs back, you're going to see, oh, look, this actually turns back into the original equation. Okay, and so you'll discover that this is in fact an odd function. Okay, and remember, odd just means that you have origin symmetry. Odd is a descriptor for the function, while origin symmetry is a descriptor of what kind of symmetry your graph would have. So let's take a look at this next one down here. So again, 3x squared plus 5. That's my original. We're going to see if we can match to that. So we're going to plug in negative x first. That's if my function is even. So y equals 3 negative x squared plus 5. Okay, and let's go ahead and simplify this down. So of course, the square is going to cancel my negative. Y equals 3x squared plus 5. And you can see, hey, that is in fact the original equation. So this looks to be an even function. And a little bit of an odd tidbit, being even does not necessarily preclude you from being an odd function. So we'll test both ways just in case. Okay. There are some shortcuts to this, however, guys. If you notice that all of the powers of x here are even, including the 5, which is an x to the 0 power, okay? And that is kind of a giveaway that this is going to end up with an even result, okay? because all of the x powers are even, okay? But when we set this up using negative y, you're going to see, oh, this is not going to work out, just like we already saw it. So negative y equals 3x squared plus 5. And this is, of course, not the same because of that negative sign. So we'll just say nope. So this one is an even function, not an odd function. Okay. Again, you're looking for which way it will match up and be the same as the original. Okay. Okay. So if you consider a function, and they kind of are telling you about what I just mentioned, that if you see only even exponents, including x to the 0, right, which is a plain number, it will always be an even function. And if you see only odd exponents, the function will be an odd function. And so you can kind of use that shortcut to help you with this a little bit.